Swayam Prabha. Digital India. Educated India.
Okay, so let's continue our discussions related to this particular course, Introduction to Electronics. In this lecture number 28, we'll look at transistor circuits. And if you recall that in the last couple of lectures, we had seen how we can take a three-terminal device, a unilateral device, and despite some non-idealities in the characteristics of that particular device, how we can construct an amplifier. And so we had taken a general, a hypothetical element like three-terminal element like Z here, whose characteristics are shown, I0 versus input voltage here, and I0 versus output voltage here. And we had seen this particular schematic here. The purpose of R1, R2, RD is to bias this particular device in a suitable region such that it is capable of amplification. The purpose of RS0 was to make the circuit stable against variations in R1 or variations in VDD here, and the signal is applied over here, and the capacitor is required in order to apply the voltage here properly to the input here, and this particular capacitor is required to block any DC from going to the output here. And so anyway, we had looked at the details of how this particular schematic originated. And now what we can do is we can take this element Z out, which was a hypothetical three-terminal element here. We can replace it by a transistor, a bipolar transistor, or we can replace it by a MOSFET. And we'll get these amplifiers here, where, for example, we've taken a bipolar transistor here. So this is a BJT amplifier, and it's also called there are various kinds of BJT amplifiers. This one is also called a common emitter amplifier here. And if we replace this by a MOSFET, N-type MOSFET here, we'll get this kind of an amplifier here, which we also call as a common source amplifier. So let's focus our attention on MOS amplifiers, MOS circuits, because they constitute the majority of the circuits that are used at present. All right, so this is the schematic of the MOS amplifier. The same schematic that is shown over here is depicted here also. So as we discussed, the purpose of this particular whole amplifier is to take this particular signal here, amplify it, and we're talking about voltage amplification, and the amplified voltage has to appear across the load resistor RL here. And the rest of the circuit is all, because the transistor is non-ideal. It has non-ideal characteristics. It's not like an ideal transistor. The purpose of R1, R2, RS, RD is all to bias this particular transistor in an appropriate region. So the purpose of RS is to make the circuit stable against variations of R1, R2, RD here. And so we'll simplify the circuit further by removing these effects here. Okay, removing RS and CS here. And if the characteristics of the transistor are not very sharp, the requirement of RS and CS are not that essential. And so we obtain a simplified amplifier schematic, which is shown over here. All right, so we need to, our interest is in determining, for example, given, let's say, R1, R2, RD, RL here, our interest is in determining how much is the voltage gain of this particular amplifier, okay? And so when we see circuits like this, amplifier circuits like this, we notice that there are two kinds of voltages. There's a DC voltage here applied, the purpose of which is to bias the transistor in the suitable region of the characteristics. And then, of course, there is the signal here. And the signal, we said, can be an audio signal, can be a video signal, could be anything. But just for the sake of discussion, we'll be taking this as a sinusoidal signal here. So there is a DC analysis, and then there is a AC analysis, or we also call, because the signal is small, we also call that is the AC small signal analysis here. And so the goal is to calculate AV equal to V0 by Vs. So the first thing that we do is we carry out a DC analysis here to find out where is this particular transistor biased, in which part of the characteristics is it biased here. And so when we do the DC analysis, of course, we remove the capacitors are open circuit here. So when this is an open circuit, RL goes away. When this is an open circuit, VS goes away. So we are left with this particular circuit here. And we analyze this particular circuit to determine how much is the DC current flowing through the MOSFET here. What is the voltage at this particular point? We'll see examples of this in today's lecture. And once after we have done with this DC analysis, then we do what we call AC or small signal analysis. And when we are doing that, then we remove the DC sources. So removing the DC source, which means that this VDD here becomes ground here. Note that when we write VDD here, it means that there's a battery equal to VDD connected between this node and ground. And so VDD gets shorted here. The capacitors, we assume that the values of the capacitor have been chosen such that the impedance is very small. So we short this particular capacitors here. So we get this circuit here. And so we need to analyze now this particular circuit to determine V0 by Vs. And here, when we analyze this, we need a DC model of the transistor. And here, when we analyze the circuit here, this is a different kind of analysis. We need an AC or a small signal model of the transistor here. And so let's look at those models of the MOSFET here. So we said MOS can operate, it's a slightly complicated device. There are two broad regions. First, there is a voltage called threshold voltage here. Sometimes you'll see the symbol here VTHN and sometimes VTN. So both of them are the same. And so MOS, you can operate it above threshold or below threshold. So threshold voltage is an important voltage which distinguishes two operating modes. And so note that in this case, the characteristics that is shown is ID versus VGS. And the threshold voltage is 1 volt here. And so below 1 volt, the current is not 0, but very small here. In fact, you can see it from this particular characteristics here. This is ID versus VGS linear characteristics. This is ID is plotted on a log scale versus VGS here. So threshold voltage is somewhere here, 1 volt. And so below 1 volt, the current is there in a MOSFET, but the current is small. You can see here 1 microamperes, 100 nanoamperes, depending on how low you go. And so the current is small. And if we want to develop a very simple model for a MOSFET, we can say that the current below the threshold voltage is negligible. But keep in mind, negligible and all that depends on the application that you're looking at. And this is the accurate picture. Below threshold, the current is small, but it is there. And it keeps on decreasing as we go to lower and lower gate voltages here. So that's the subthreshold part here. Above threshold, above 1 volt here, this is the characteristics here. The current flowing through the MOSFET is significant. Above threshold, which means that the MOSFET is in strong inversion region. And most of the amplifiers are constructed for VGS larger than the threshold voltage here. So for our course, we'll assume in most of these cases, when we build amplifiers, we'll take VGS greater than VTH here, or V threshold voltage here. Once it is above threshold, there are two regions again that the MOSFET can operate in. One is the saturation region where the current is, so note that this is IDS versus VDS characteristics. Drain to source current versus drain to source voltage here. Drain is here, source is here, and gate is here. So in saturation, the current is changes very little with the drain to source voltage here. While in the linear or triode region, the current is changing significantly with the voltage here. And we call it linear region again because close to VDS equal to 0 here in this part, the characteristics is linear. And the dividing line between the two regions here, linear and saturation region, is given by this voltage called VD sat, saturation voltage here, whose value is equal to VGS minus VTH. Okay, so that decides whether the MOSFET is operating in saturation region or linear region. So for amplifiers, most of the time what we will look at is our transistor will be biased above threshold. And for constructing amplifiers, we want to be in this region. If you recall a discussion related to amplifiers, we wanted output characteristics to be flat like this here. Okay, and so we want to bias a transistor in this particular region. So let's look at the DC. So this is our MOSFET here, the structure of the MOSFET. And this is the cross-sectional view. If we take a cut through the device, So we'll see that there is a metal, there is an oxide, there is p-type semiconductor, there's N plus and N plus here and all that. This is the top view of the device. So this N plus that you see here is this region here, source. This other plus is the drain here. In between is the oxide and all that. So this is the gate part here. So this is the length of the MOSFET here. The separation between source and drain is what we call as the length. So from here to here is called the length here. And then the width of the MOSFET is here, right? So this is the width of the MOSFET here, okay, W. And these are not important for us, the length of the source and the length of the drain right now. They determine capacitances and other things that are there. So when I look at a MOSFET and I look at it in a DC case, note that the only current that can flow in a MOSFET is between drain and source. A gate, there's an insulator, so it doesn't flow here. And body or substrate to N plus or body to drain here, both of these PN junctions are reverse biased. So no current flows here. So the only possibility of current is between source and drain. And in any case, we said that the body we will consider it to be grounded, and we will not show explicitly here. Body and source will be grounded, so we'll not bother. Body and source are shorted together, so we'll not show it explicitly here. So we'll look upon MOSFET as a gate, a drain, and a source here. And the only current that can flow is between drain and source. And that current is the drain to source current. And if we are biased in saturation region, then the current can be expressed as IDS equal to beta n by 2, VGS minus VTHN square, where beta n is equal to Kpn W by L. So Kpn is an important parameter of the MOSFET. It's called the transconductance parameter. And once you choose a MOSFET from a particular manufacturer, then the Kpn value gets fixed here. But as a designer, and what we have under a freedom is we can choose W and L under certain constraints. So L is something that you can, when you're designing MOSFET circuits, you can choose L. If let's say the manufacturer may tell you that the L minimum value is, let's say, 0.5 micron. Then you can choose L anything above 0.5 micron, W anything above 0.5 micron here. So W and L are important design variables. We can alter the values of W and WL. But Kpn is fixed. Once you choose a particular technology, particular MOS technology, Kpn gets fixed here. So that's the model of the MOSFET in saturation region. So you are given a value of Kpn, and if W and L is also given to you, then you know the value of beta n, and threshold voltage will also be given to you. So you can determine the current depending on the gate to source voltage that you apply. The small signal model of the MOSFET, or the AC model of the MOSFET, is shown here. So all AC or small signal quantities will be shown in small letters here, G small, S small here. So again, between gate and source, we have nothing here because there's an insulator here. Between drain and source, we have a dependent current source, GM times VGS, and we also have a resistor R0 here, output resistor. If you recall our discussion, we said that any three-terminal linear device, unilateral device, could be represented in this particular form. In more general case, there was a resistor here, but in this case, the resistor value is infinite. So the GM, the transconductance that you see here, can be expressed as 2IDSQ VGSQ minus VTHN, or square root 2IDSQ times beta here. So note that the small signal parameter GM, or the AC parameter GM, depends on the DC current or DC voltages across the MOSFET. So the value of GM is the bias point or the quiescent point or the DC current flowing through the MOSFET here, and the DC voltage across the MOSFET here, VGS here. Okay, so that's why we can only do small signal or AC analysis of the circuit after we have done a DC analysis. So we have to do a DC analysis to figure out what is IDSQ, what is VGSQ. Then we can determine GM. And R0 is 1 over lambda times IDSQ. Lambda is called the channel length modulation parameter. We'll not bother much about it. In most of our analysis, we'll take, in most of the cases, we'll take lambda equal to 0 here. Although it's given 0.01, we'll take most of the time lambda equal to 0 here. So R0 for us will be almost infinite here. So that's the small signal model. So if you're doing small signal analysis of the MOSFET, all you have to do is take the MOSFET out and substitute this particular model. And to use this particular model, you'll need a value of GM. And to need the value of GM, you need to know the DC current and the DC voltages across the MOSFET. Our MOSFET, as I said, many times it will be here in saturation, but if you have not designed the circuit properly, or for some specific reason, you may bias it here also in the linear, or it's also called the triode region here. And if you're in this region of the characteristics, note that how do we decide whether it's in this region? Well, your drain to source voltage has to be less than VDSAT, VGS minus VTH. So in this case, the MOSFET characteristics depends on VDS, unlike here where it's independent of VDS. Here it depends on VDS and is given by this equation here, beta n, VGS minus VTH and VDS minus VDS squared by 2. And in most of the cases, just because it's a nonlinear equation, it's a quadratic equation, depends on VDS square. Most of the time, what we'll do is when we consider triode region, we'll assume that we are in this particular part here, where the characteristics is linear, which means that the square term can be neglected. So whenever we have to analyze our circuit, and if we find that the transistor is working in this particular region here, triode or linear region, we'll assume that the quadratic term is negligible. So we'll use IDS equal to Kpn W by L. That's nothing but beta n. VGS minus VTHn into VDS here. So we'll use this simplified expression for analysis in this particular course. Knowing that if we want to do more accurate analysis, we can consider this also. There's no conceptual difficulty, except that to keep analysis simple, and we'll use this particular expression here. So one of the slight difficulties that we face when we analyze these transistor circuits is which mode is the transistor operating in. It's just like with diode circuits also. We have to decide, is the diode forward bias or reverse bias? So unlike passive components like resistors, capacitors and inductors, they have the same value, constant value. But in these cases, we have to determine which mode is the device operating in. So let's look at this particular case here. Suppose we are given a MOSFET with 2 volt applied to the gate, 0.5 volt to the source, 0.7 volt to the drain here. And VTH in almost all cases will consider 1 volt. So we want to know, first of all, is the diode in above threshold or below threshold, right? So, and if it is above threshold, is it in saturation region or is it in triode region? Okay. So first of all, we note that to determine whether it is above threshold or below threshold, we take VGS. So 2 volt gate and source is 0.5. So VGS is 2 minus 0.5 is 1.5. So 1.5 is larger than VTH. So we are above threshold. All right. The next thing is we have to figure out we are in saturation or triode. So VGS is 1.5. 2 gate voltage minus source voltage 1.5. VDS is 0.2. VDSAT is what decides whether it's in saturation or triode region here. And VDSAT is VGS minus VTHn is 0.5. So our VDS is less than VDSAT, so we are in the linear region here, in this particular region. So that's how we figure out. So now we can, if we want to find out current flowing through the MOSFET, we can use the expression for current in the linear region of the characteristics. So let's look at the same device, but we have raised the drain voltage to 1.5 volt. So now VDSAT is 0.5 again. VDS is 1 volt here. So obviously it is in saturation region here. All right, so suppose we are given a transistor like this here. So is the transistor in linear or saturation region? Note that the gate voltage is also equal to 2 volt and 2 volt VGS is 2 volt, larger than 1 volt here. So it is obviously above threshold. So VGS is 2, VDS is 2, and therefore it's in saturation region here. Why? Well, because VDSAT, what is the saturation voltage here? VDSAT will be equal to VGS minus VTHn, which will be 1 volt, and VDS is greater than that particular value here, than VDSAT here. What about this? So note that this is 1 volt, this is 0.5 volt. So 1 minus 0.5 is 0.5 volt here, which is less than the threshold voltage here. So my transistor is in subthreshold mode of operation here. Okay, so we are somewhere over here in the subthreshold region here. Okay, so let's solve some circuits here. So we have a transistor circuit given here. The bias is 3.3 volt here. Note that when we write VDD equal to 3.3, it means this node is connected through a battery to ground via 3.3 volt here. And so we are given KPN, transconductance parameter, VTH and 1 volt. So we'll take these as constant everywhere in the circuit. So we're asked to determine IDS and VDS. What is the drain current flowing here? And what is the drain to source voltage here? So the problem again is my transistor in saturation or triode region? So given like this, we don't know what is the value of drain to source voltage here. And therefore, it's hard to figure out, is the transistor in saturation or triode? So what we do is we assume. Let's assume saturation mode of operation. You have to start by assuming either linear or saturation, okay? So let's assume saturation mode of operation. Once we assume saturation mode of operation, this is the expression for current. And so we are given everything, Kpn, W by L. Note when we write 2 by 1, it means W is 2 and L is 1. The ratio W by L is 2 by 1 here. And we are given everything here, VGS minus VTH. And so we calculate IDS is 10 per minus 4 amperes. Once we calculate IDS, we can calculate the drop here and we'll know what is the VDS here. So VDS is equal to VDD minus IDS RD, so 1.2. And VDSAT is VGS minus VTH and equal to 1 volt. And since VDS is greater than VDSAT, so our assumption is correct. We assume saturation mode of operation and we find that our assumption is correct. So all these values that we calculated are correct. So the problem is solved. We know the drain current is 10 per minus 4 amperes. Drain to source voltage is 1.2 volt here. Well, let's look at the same example, but where instead of 20K, we've put 35K here. Suppose we did the same thing. Assume saturation mode of operation, same current here. We calculate VDS equal to VDD minus IDS RD and we obtain minus 0.2. So minus 0.2 obviously is incorrect. So our assumption is incorrect, which means that the transistor must be operating in linear. There are only two possibilities, triode or linear or saturation. So next we use an expression for linear. So linear expression is Kpn W by L VGS minus VTH and into VDS. And VDS is VDD minus IDS RT. So we solve these two equations together. These are simple linear equations. We solve them together and we obtain IDS is 8.25, 10 per minus 5 amperes, VDS is 0.412. And note that if we calculate VDSAT is VGS minus VTH in 1 volt, VDS is less than VDSAT, so obviously it is correct. Our assumption of linearity is correct. And we didn't even have to check in this case because we had proved that it is not in saturation, and it's not in saturation, then the only alternative is the linear or the triode region here. All right, example 3. So we have this circuit here. Note that it means W by L is 5 by 1 here, and we have to determine IDS and VDS here. So in this case, we had already seen that when gate and drain are shorted together, the transistor is always in saturation. So there's no issue about that. So VDS equal to VGS, VDS is then greater than VGS minus VTH, and so it's in saturation. So we have this current here. IDS is Kpn W by L, VGS minus VTHN squared by 2 here. But note, what is the value of VGS? Gate voltage we know, but VGS would depend on this value of the source voltage here. And the source voltage here is nothing. The same current IDS flows here. So VGS will be equal to 3.3 minus IDS into 18 to 10 power 3 here. So IDS into 18 to 10 power 3 is this source voltage here. So that's VGS. And we have to solve these two equations together. And so a little bit involved because we have a square term in here. But if we solve it properly, we may get IDS is 2.48, VGS is 1.315 here. And so when you have a quadratic, you may obtain maybe another solution here. You may find that if you solve the quadratic equation, you may get VGS equal to 0.653 also, which is not possible because note that for current to flow, VGS has to be greater than VTH and 1 volt here. So this particular solution, although mathematically we get that, but this particular solution we have to reject because it's not possible here. Okay. And note that for VGS equal to 0.653, this equation is also invalid here because this equation is only valid when VGS is larger than VTH in here. All right, so you have to reject this particular one. All right, so let's take up a simple amplifier. So we have a circuit which is very similar, but in addition to the DC bias and everything, we have a sinusoidal source or a signal that we want to amplify. And in this case, we have taken lambda n equal to 0 here. Okay, so our goal is to find out the voltage gain, V out versus VS here. But this V out versus VS is a AC gain or the small signal gain. And before we can do small signal analysis, we have to do the DC analysis here. okay, DC or bias point analysis. So for that, we remove this particular one. Capacitor is open circuit, so we get this circuit here. Note that W by L is 20 by 1. So we've already solved a circuit like this, okay. IDSQ, we assume it to be in saturation, so we get 90 microamperes of current. We calculate VDSQ, so we are now calling it DC current. Also, we are adding a Q here to denote that it is the bias point or the quiescent point here. VDSQ is VDD minus ID squared, is 1.5. VDSat is 0.3, so 1.5 is greater than 0.3, so transistor is biased in saturation region. So we know IDSQ and we know VDSQ here. So once we have done the DC analysis and we know IDSQ, we know it is in saturation region, then we go to AC or small signal analysis. And in that case, we remove the bias here, we remove this bias also, we short it, we short this here and short the capacitor here. So we obtain this particular circuit here. All right, so this is connected to ground, DC is removed, capacitor is shorted here. Now we have to use a small signal model of the transistor, which is this one here. Small signal model of the transistor or AC model of the transistor is GM, VGS and R0. And R0 was equal to 1 over lambda times this, so R0 also disappears for us, it's infinity. Okay, and GM is 2 IDSQ, VGSQ minus VTHN, or same 2 IDSQ times beta here. And we have already determined the DC current here, the quiescent value or the bias point here. That's why we do the bias analysis first to determine the value of GM. So we know the GM also here. And R0 is infinity. So now what we do is we take this transistor out, substitute this particular model, and then calculate V out by Vs. All right, so this is where we are. And so we take this particular model here, remove the MOSFET and substitute it here. And then we can also simplify RD is parallel to RL. We can combine these resistors and put it over here. And so this is what we obtain, a very simple circuit. And so we know that VGS will be simply equal to Vs. And so this current will be equal to GM times Vs here. And this current will flow through a parallel combination here. So V out by Vs is equal to minus GM, RD parallel RL here. And if we put in the values of GM that we had calculated here, RD parallel RL, we get a gain of 10. Of course, there's a 180-degree phase shift, and we get a voltage gain of 10 here. So that's how we analyze circuits, amplify circuits. First, we do a DC analysis and determine the bias point. And using the bias point, the DC current, we determine the value of GM here and R0 if required. And then when we do AC analysis or small signal analysis, we substitute this particular model here for the transistor. And then we get a linear circuit and we determine the ratio V out by Vs and we get the value that we're looking for. All right, as a last example, let's look at a circuit which is of interest to us because this leads us to digital circuits. And so it's a similar kind of a circuit here with a supply here, RD here, transistor, and what we are looking for is V out versus V in characteristics here. So what we are going to do, what it means is we'll start V in from 0 and we'll go all the way up to the supply voltage, which is 3.3. And what we would like to know is what happens to this relationship between V out versus V in. So on y-axis we have V out, and on x-axis we have V in. All right, and of course we need to keep in mind KPN and all that is given here. We need to keep in mind that ID versus VGS characteristics is like this here. Okay, and so below threshold voltage of 1 volt or so, we'll take current as negligible. The current of course is flowing but is small, and so we'll take it as negligible below threshold voltage. And we also have to keep in mind that above threshold voltage we have saturation and linear region. So when we start off with, let's say, V in equal to 0 or 0.1, what would happen is that 0.1 or 0.2 is less than the threshold voltage of 1 volt. So the current is negligible. The current is negligible here. So the voltage drop is negligible. So V out will be simply equal to VDD, which is 3.3. So that's how we start off with. Okay, we start off with VDD equal to 3.3 here at this point. And this will continue till we cross the threshold voltage here, 1 volt. Because once we cross the threshold voltage, then significant current starts to flow here. And if current starts to flow here, there will be a voltage drop here and V out will become less. V out is equal to VDD minus the voltage drop here. So V out will become less. And in general, it will, so this is the boundary line here. And after that, it will go something in this particular way here. And note that it will start off with my circuit in the saturation region first. Why? Because when we are at, let's say, Vn equal to 1.1, when you Vn equal to 1.1, so we are above threshold and our current would flow. But note the value of the current depends on VGS minus VTHN. So the current is still small. And when the current is small, the value of this voltage is large. And therefore, when the value of this particular voltage is large, we are in this particular region here. Vout is nothing but VDS. And VDS will be much larger than VD sat here. So for example, if this is 1.1, so VD sat for us is 1.1 minus 1, so 0.1 volt. And VD sat is 0.1, and the drop here is not that large. We can calculate how much it is. And Vout will be considerably larger. Maybe we are here, let's say Vout is 3 volt or 2.5 or so. So we start off in saturation region. But as we keep on increasing Vn, the current keeps on increasing and this voltage VDS keeps on falling. And eventually we go into linear region here, right? So we start off with saturation. So this is like cutoff. Cutoff meaning the MOSFET is in the cutoff state or open circuit mode, very low current mode here. That's what we mean by cutoff, low current mode here. It goes into saturation, then it goes into linear. And the boundary we can determine also using these equations here, right? So boundary means that Vout is exactly equal to, we are at this point. So Vout is equal to VD sat equal to Vin minus VTHN. And we also know Vout is VDD minus IDS RD. And IDS is KPN W by L, VGS minus VTHN square by 2. So we are talking about, we are a little bit left of the boundary here. So saturation current is still valid here. Now we can solve these equations together, and we'll not do that here explicitly here. 1.58 volt we'll get here. Now, if you go beyond 1.5 volt, of course, the current keeps on increasing, but the transistor is in linear region. And we want to know what happens when it goes to 3.3 here. So at this particular point here, 3.3 here. So when we apply 3.3 here, what happens is that the transistor goes deep into linear region. We are somewhere over here, okay? And we can calculate now what is the current using this expression here. So we use the linear expression. IDS is KPN W by L V in minus VTHN multiplied by Vout. And Vout is VDD minus IDS RD. So these two equations, these are two linear equations, we can solve them up. And if the solution is correct, we obtain 0.087 volt here, right? So this is what happens when we increase Vin from 0 and we go all the way up to the supply voltage 3.3, Vout goes in this particular manner here. And so note that when Vin, so what it says is when Vin is small, when Vin is close to 0, output voltage is large, 3.3. And when Vin is large, 3.3, output voltage is very low, 0.087. So this acts like a digital NOT gate here. We also call it an digital inverter because when input is low, output is high. When input is high, output is low. So it's called an inverter. And also it's a NOT gate here, digital NOT gate here. So that's how we build a one way of building a simple digital gate here. And if we add more transistors, if you're familiar, we can build a NAND gate. For example, if we take one transistor here and we add another transistor here, we'll build a NAND gate. If we build two transistors in parallel, we can build a NOR gate. So all of those gates we can build using these MOS transistors. So let's stop here.